Hey everybody, my name is Taylor Sparks and I'm the Editor-in-Chief at Integrating Materials and Manufacturing Innovation. Today, I'm here to talk about the paper, Computational Design of Alternative Binders for Sintering of Tungsten Carbide Hard Metals. This paper comes to us from Molla, Jonsson, and Schaffer at the University of Melbourne. And the key hypothesis that they're setting out to answer in this paper is whether or not we can use computational methods to aid in the design of new binders, right? Materials like tungsten carbide, right here, they're used for lots of applications, cutting tools, for example, but they predominantly rely on cobalt, right? In fact, I remember when I bought this, it was a cobalt bonded tungsten carbide ring. And the problems with cobalt, well, there's safety and ethical issues when it comes to using cobalt. We would love to use other materials that aren't cobalt, but the process of exploring them, they point out, has been predominantly trial and error, prototype and then test approaches, which are not efficient. So what they're going to try and set out to do here is assess whether or not they have a formulation methodology for finding new binders, which are based off of analysis of, yes, mechanical properties, because it does need to be hard, but also processability. And that's going to have to do with how we sinter these particles together, right? So they're putting forward this new approach, finding new materials by considering both processing and properties simultaneously. The way they do that is going to be with multi-objective optimization, coupled with reduced order models based off of thermodynamic and kinetic properties. Now, this work does build on some previous work. For example, references 5 through 9, they identify a number of different alternatives to cobalt, iron, nickel, and alloys of the same that have been explored in this 1987 publication. So let's talk more about their approach. So how do we account for the processability? Well, as a ceramist myself, I know that oftentimes when you're sintering materials, a little bit of a liquid phase really helps achieve much higher hardness. And not surprisingly, in this work, they talk about that as well. You've got Schubert and Garcia both suggesting that in these tungsten carbide hard metals, having a little bit of this FCC austenite phase or a little bit of liquid or both is really beneficial. So for example, what you're seeing here is a calculated phase diagram for a 3-component system, tungsten, cobalt, and carbon. And what you're seeing here on the x-axis is the amount of carbon present holding the cobalt concentration at 10 weight percent. And sure enough, you see that there does exist a region here in the middle where you've got liquid, FCC, and tungsten carbide. So what they're going to be doing in this approach is using calculated phase diagrams like this, the CalFAD method, to calculate regions and identify regions where you have a composition and an appropriate processing window at the temperatures of interest. In fact, in the paper, they really get into the details of what's happening during sintering, right? Obviously, there's consideration of surface energies, there's diffusion that has to take place, there's free energies that they account for, and they do a pretty good job of capturing the different kinetic and thermodynamic parameters that should be related with improved sinterability so that you can actually process these things effectively. But apart from just being able to process it effectively, it has to have the right properties, right? Hardness is the primary one they're looking at here. And they obviously point out that there's been a number of models used. Ultimately, they're talking about the Walbrule model. This is essentially a comprehensive one, accounting for the hardness of multi-component alloys using expansion similar to the Gibbs energy in thermodynamics used in the compound energy formalism. This is essentially capturing things like solid solution hardening, so it should give you a feel for the hardness. So we now know we have a proxy for both the hardness and a proxy for the sinterability. Again, the approaches used are computational thermodynamics. So they use the thermocalc software, which is based on the CalFAD method, calculated phase diagrams. And since they're considering multiple objectives, they're going to tackle that by using the non-dominated sorting genetic algorithm, very popular genetic algorithm used in lots of fields, the NSGA2. This is going to allow them to consider both processing and properties at the same time. If you're not familiar with this genetic algorithm approach, essentially it starts with some initial population of candidates, and on the very first iteration, all they can do is they define this as the initial population. They do the CalFAD calculations, and they ask whether or not the microstructure has the phases that they're interested in, right? A little bit of a liquid or an austenite phase. If yes, then they continue forward, and now they identify their 2 objectives, right? The sinterability, the binder hardness, right? Then they take this population, and if it's less than their desired number of populations for this, population to go forward, they then ask, does this meet our stopping criteria? Is it good enough to be a new binder, essentially? If yes, then they're done, right? If it's not done, then you go back and you add another iteration. Now your parents are equal to the former population and you've added to it. So at this point, you can now have the parents do crossover, mutation, randomization. This is the reproduction part, which is going to create new offsprings. You ask them, do they meet the thermodynamic calculations? If so, right, they've got the right phases present. Now you assess their sinterability, binder hardness, and you repeat this process until you've reached your stopping criteria in terms of the size of the population, number of iterations, or having the right properties of interest. And then you can plot these. So they put this to work, and what they find can be summarized here in this figure, right? What you're seeing here is a comparison of the simulated densification trajectories against actual experimental results from literature. So you can see how well these actually track for, say, nickel-based or iron-based materials that's going to help them try and find new materials. So what were the real takeaways? You can see for yourself. On a plot like this showing you both the sinterability and the hardness, we can find actual new materials, and they have reduced cobalt, or in some cases no cobalt, right? Iron, nickel, molybdenum, for example, or the iron, nickel, moly, cobalt system, where you're getting sort of improved possibilities by doing this computational based approach.